It is the 6th of September in the year 2017. So we looked at using dimensional analysis. Why do we use dimensional analysis? To see if we've made a dumb mistake. To see if our rearrangement, our algebra, is good. We can evaluate an expression and evaluate an answer and make a prediction another way too. So using dimensional analysis lets us know, you screwed up your algebra, look at that. Okay. We can do what are called order of magnitude estimations, also called Fermi estimations, also called Fermi problems or Fermi questions. And what we do is look to see, it's a ballpark. In what ballpark should our answer be? And we do it using powers of 10. It's named a Fermi estimation for the physicist Enrico Fermi. Fermi Labs in Chicago is named for him. He was a Italian particle physicist, worked on the Manhattan Project. And one of the things he was famous for was the ability to give these fast, off-the-cuff answers. How many hot dogs are eaten in a year in the United States? And Fermi can go, well, let's see, 10 to the 3rd, 10 to the 6th, 10 to the... 10 to the 9th. And then when people would go get an actual answer, Fermi typically was in the ballpark. Ballpark, hot dogs, get it? No, never mind. So what we're looking for in a Fermi is just what power of 10 is closest to the true value of the number, each number in the expression, what power of 10 is closest to the actual answer. And what it gives us is our answer reasonable? It doesn't tell us if our answer is right, but if our Fermi estimation says, well, I would expect that the answer to that would be order of magnitude 10 to the 4th. And we get 37 as an answer. We're going to need to question our problem-solving methodology because these two things don't line up very well. If we do an estimation and figure, well, our answer should be magnitude 10 to the 4th, and we get 9,763. We're like high 10 to the 3rd, low 10 to the 4th. Okay, it might not be crazy. We might be in good territory here. It's just a way to check the reasonableness of your answer. It is not in and of itself an art form. It is not in and of itself anything. And here's the part that nearly made a very dear student's head explode many years ago. There often isn't a right answer for a Fermi. There's a right process. And so with Fermis, a lot of the key is showing your process. So I want to show you a quick video that somebody who's way more clever than I did about Fermis and how we do them, and then we'll practice some. Okay, so we're going to do a Fermi estimate of the number of piano tuners in Chicago, and we just did this, okay? They did it, but they sort of did it as a black box mystery thing where they just tossed numbers up and magically did the math, and they didn't really show you the process. So I'm going to show you a little bit how I sort of fight with the process because I tend to screw this up. I say that a lot. I always have to work really hard and look really carefully so that I am using those powers of 10 correctly. Okay? So I tend to start off with what I want to know, sort of set up as a fraction. So I'm looking at piano tuners per Chicago. And that's going to help me know whether I need to multiply or divide my powers of 10. So I'm going to do some sort of rough stuff. I know that I want to end up with number of tuners in one Chicago. You didn't know that one Chicago was a unit. Surprise! So it would be helpful, I think, to know, and this is where they started, with people per Chicago. Okay? And they were estimating that the order of magnitude of the population of Chicago was 10 to the 6th. Okay. So you have 10 to the 6th people per one Chicago. Well, now they want to know how many pianos per people. And they came down to one piano per 10 to the 2nd people. Boy, that's terrible handwriting. I apologize. Let me fix that. So if we use sort of the logic that we've been using for factor labels, what did we just do? We canceled out people, so now we now are looking at something that gives us a very rough order of magnitude estimation of pianos per Chicago. So now, and they did this a little bit differently. I have a hard time wrapping my head around the way they did it. I guess they did pianos tuned per year. So they were saying that one piano tuner tunes about, 100 pianos a year? So they said so one tuner can tune 10 to the second pianos. So now, if we follow that logic, we're getting rid of pianos, and good grief, look at that. We're now down to tuners in Chicago. So we've got 10 to the 6 minus 2 minus 2, which gives us that 10 to the second tuners in Chicago. Okay. Physics Olympics, that much heralded, it is actually a lot of fun, and like I said, it makes scones. Competition in February. They have an event called the Fermi, and you get a team of 3 people, and they go into a room, and they're handed a sheet with a bunch of questions to which Fermi estimates can be given, and the teams, I forget, if they get the same order of magnitude as the most common answer, it's like 5 points, and one order of magnitude off in either direction is 4, and down, or 2, and then down to 0. So there is a website called Fermi Questions, and it's a random Fermi question generator. So let's actually look at a few of those together, and then we'll do, I want to skip that, let's see. Oh boy, okay, this is a good one. Well, the way that the Fermi site works, you move this slider up or down once you come up with your answer, and when you submit it, it then compares it to millions of answers from other people and looks at how many orders of magnitude off you are, which is kind of convenient. So we'll do this together, then we'll submit it and see how far off we are from the most common answer. Okay, so what we want to know is tennis balls per General Sherman. Okay, seems easy enough. If you set it up as a factor label, that gives you sort of something to hang your logic on. So, where do we start? We're looking at mass. They say weight. Ridiculous. Let's see. Mass per tennis ball, grams per tennis ball. Let's see. 10 to the negative second, 10 to the first, 10 grams. 10 to the first sounds reasonable to me. So let's see. Actually, you know what? This is even easier than that. So if we say that mass of one tennis ball, so 10 grams. Oh no, see, this is where I get all confounded. Okay, so 10 grams per tennis ball, so 10 to the first grams per tennis ball. Well, grams of General Sherman. So this is the world's largest tree. 10 to the second, 100 grams. I've bought more cheese at the deli counter. 10 to the third, 1,000 grams. That's 1 kilogram. Just for reference, in Europe, if you walked up to a deli counter in Germany or Poland or France, you would probably be asking for a kilogram of cheese. That's a reasonable measure of cheese to buy at the deli counter. So General Sherman probably weighs more than a reasonable amount of cheese to buy to pack sandwiches for the week. 10 to the 4th? That's like 10 times the amount. Okay, so that's 10 weeks worth of sandwich cheese. 10 to the 5th. I'm gonna take a wild guess, and I'm not actually, I don't know the number. I don't know the number. That's one of the things you have to deal with these is you are uncertain and you have to be okay with uncertainty. I'm gonna say we're probably looking at something like 10 to the 7th, like 10 million grams in General Sherman. That's a, you know, I can't imagine that it's 100 million grams. And admittedly, I have a handicap as an American where outside the deli cheese example, it's hard for me to think in metric. So I'm going to say 10 to the 7th grams, which would be 10 million. 10 million grams? Does that sound like enough? Let's try that. Okay. So if that's the case, then we cancel out grams, and guess what? We're left with tennis balls per General Sherman. Cool. So we're going to submit our answer to the interwebs at large and say that it would take 1 million tennis balls to equal the mass of General Sherman. Now that doesn't sound like enough for me. I think I screwed something up. I think I went low on my estimate of General Sherman's mass. I think General Sherman weighs more than that. But let's see what, this is like Family Feud survey says. So I'm going to submit 10 to the 6th. Fermi answer, most common and best answer, considered most correct, is 10 to the 8th. So we are 2 orders of magnitude off. And that's due to a lack of knowledge on my part. Because I don't really know what General Sherman weighs, and I'm doing a bad job estimating that. Let's try to get one where we can, hold on, let me pause this. 1 micrometeorite, a sphere with a distance of, the diameter of 1 times, okay, so 1 micrometeorite struck each square meter of the moon each second. It would take many years to cover the moon with micrometeorites to a depth of 1 meter. Consider a cubic box, 1 millimeter on a side, on a moon. How long would it take to completely fill the box with micrometeorites? Where do we start? Well, whoops. Best place to start is, I know, I seem to have a bias about this, but what we're looking for is, let's see, would it be time per box? Time to fill the box, or would that be boxes? Yeah, time per box. And I do find that these help me organize my thought process. Okay, so I guess first of all, we got to figure out how many seconds. Yeah, let's change that time to seconds. So seconds per box, because we have seconds in the prompt. So 1 micrometeorite strikes each square meter of the moon. Well, I'm going to approximate. So I've got this little spherical micrometeorite. I'm going to approximate it as a cube. That's easy. So it's got a volume. We have the volume of the micrometeorite. I have the volume of the box, and I have the micrometeorites per second. And I'm intentionally putting these as all sort of disjointed things because I'm mentally right now working through where they go. And that's the process that I want to work on with you. So the number of micrometeorites that fill the box is going to be the volume of the box divided by the number of micrometeorites, or divided by the volume of micrometeorites. So let's rearrange that a little bit. I'm going to shrink these, move them here. And I know that the volume of the box divided by, so let's see, oh, how else could I do that? Oh, I could do that even better. Okay. Volume per box times volume per micrometeorite. I'm going to move that back this way. And then what if I do micrometeorite seconds per micrometeorite? What am I left with? I'm left with seconds per box. Okay, so the volume of one box, we're told, is 10 to the, it's 1 meter cubed. So it's 10 to the 0 times 10 to the 0 times 10 to the 0 meters cubed is the volume of the box. Okay, that's the space per box. What's the volume of micrometeorites? Well, we could get into calculating volume and using the equation for the volume of a sphere, which I've just completely blanked on. 4/3 pi r cubed. No, that's surface area. That's 4/3 pi r squared. Anyway, we're not doing that. We're doing very rough estimations. So we're going to take that sphere and assume that its diameter is a side. And if they seat perfectly, they're going to seat about like that anyway. So could we be overestimating a little bit? Yeah, we could. But that's okay because these are Fermis, so we're going to have some slop in either direction. Our goal is that the slop kind of balances out. So those micrometeorites, we are told, have a diameter of 10 to the negative 6th meters. So 10 to the negative 6th times 10 to the negative 6th times 10 to the negative 6th cubic meters. And we're told, furthermore, that one micrometeorite, micro m, strikes the moon every 1 second. So we've got volume per box, volume per micrometeorite, and micrometeorites per second. Well, if we look at the units on that, we end up getting rid of volume and getting rid of micrometeorite, and hey, we're in seconds per box. So we're probably setting this up correctly. Your book doesn't necessarily show solving Fermis this way. I kind of developed this on my own because it helps me keep track of whether I should be multiplying or dividing by something. Just like using dimensional analysis to see if your algebra is correct, here you can use dimensional analysis combined with Fermi estimation power of 10s and see if you should be on the right track. Okay, so what would we get for that? So we get 10 to the 18th seconds to fill up a box. Now here's a question for you. Can any of you conceptualize what 10 to the 18th seconds is like? Because I can't. I think that's kind of dumb. So your book gives the answer in years, and I would suggest that when you've got something that's like order of magnitude 10 to the 18th, you should convert that. So let's go ahead and see what happens if we try to take this to the next logical step. I'm going to copy this. No, not cut, undo. I'm going to copy it, not cut it. Copy. I'm going to take it to the next page. And I'm going to try to do this in one big, fat, juicy, elegant factor label. So I know that I have 3.6 times 10 to the 3rd seconds in 1 hour. And that's just 3,600 seconds, 60 seconds in a minute, 60 times 60, 3,600. I know, and if, okay. Oh, how picky are we going to be? So if we're being really picky and we want to really make this all Fermi-ish, we wouldn't even be that specific, would we? We would just say, well, 4 times 10 to the 3rd. Or we could just say 10 to the 3rd seconds in an hour, which I don't like, but if we're being really, really super fast, so we don't have to do any math. Hours in a day, 10 to the 1st. I need more space. Days in a year, 10 to the second. So let's see. That's an undershot. That's an undershot. That's an undershot. I don't like where that's going, but okay, let's try it. So we get 10 to the 0 plus 1 over 10 to the negative 18 plus 3 plus 2. So I get 10 to the 1 minus negative 18. Well, yeah, I should have done that better, huh? Let's cut that. Sorry, back up. Back up on the factor label. My apologies. 10 to the 0 plus 1 minus negative 18. To get the negative 18, I took those 3 negative 6s, put them together, just in case that's not obvious. Minus 3 minus 2. So, out of all this mess, let's get rid of that. So that's 1 plus 18. That's 19 minus 5 by combining those. So I get 10 to the 14th years to fill a box. Let's see what your book says. This is, like I said, it's like Family Feud. Survey says. This is where I feel like the book gets a little fuzzy on this. They say 3.2 times 10 to the 10th years. That doesn't sound like a Fermi to me. That sounds like there are a whole lot more specific numbers, Gesundheit. They probably put in 2.4 times 10 to the second, 3.65 times 10 to the second, or I'm sorry, 2.4 times 10 to the first, 3.65 times 10 to the second. Opinions seem to vary, and I will remind you of this periodically. I am a biologist. My degree is in biology, minor in chemistry, teaching physics. So, what's the correct answer? Ask Enrico Fermi. However, he's dead. So, no means known to science will allow you to do that. Most sources seem to say that you want the Fermi estimates to really just be big numbers, power of 10. The sort of fallback that we've used in the past in my class is this. Saying 5 times 10 to the 6th, that's okay, that's a fudge. You can have one number in there. You can say, yeah, it's midway between 10 to the 5th and 10 to the 7th. Saying 2 times 10 to the negative 1, that's too specific. You know, negative 1 is 10 to the negative 1 is a pretty small range. 10 to the first is a pretty small range. If you say, 3.2 times 10 to the first, you're specifying a number. And so my fallback position has generally been, yeah, you can use 5, but you shouldn't be sticking in like 2.4 or 3.65. That's crazy. The point is to make these fast order of magnitude. That said, you're going to practice some Fermis in your book. When you do Fermis, we'll have a Fermi FIP quiz. Woohoo! Today is Wednesday. Fermi FIP quiz probably Friday. Homework due Monday, part 1 of test Tuesday, part 2 of test Wednesday. So we can roll into chapter 2. When you do the Fermi FIP quiz and when you do Fermis on the test, show your process. If your assumptions are valid and you show your assumptions, that's where you get your points. Because orders of magnitude may vary. And I've kind of in the past graded those the way that the website does. If you're in the same order of magnitude as me, perfect. If you're 1 order of magnitude off, minus a point. And if you're more than 2 orders of magnitude off, if you show me your assumptions, that's where you can get your points. Unless you have like a wacky, crazy assumption, like what was it the one year I had some question with a pizza, and somebody claimed that the order of magnitude for the diameter of a pizza was 10 to the second. I'm coming to your house Friday. That's not how we make pizza at my house. Holy cow. So they were saying that a pizza was 100 meters across. It's a big pizza. They lost points because that's a ridiculous assumption. So when you're doing Fermis, it sometimes helps. I like to do this because I'm a visual learner. Keep one of these at your desk, and during the test and during the quiz, I'll say, here, you can have one of these, because you can look at that and say, oh, yeah, 10 to the first? Yeah, okay, order of magnitude 10 to the first, sure, that's a pizza. You know, I'm sorry, 10 to the 0. This would be 10 to the 0. You know, 10 to the negative 1 is a pizza this big. Which one's closer? 10 to the 0. It's closer to a meter than to a tenth of a meter. So, okay, with that, you got time to work on homework. Not much, but a little bit. And questions. Who already wants to be on the Fermi Olympic team? I know. It took me about 3 years to stop hating Fermis after I started teaching physics, and then I grudgingly accepted them. And then a few years ago, I had like a religious conversion, and I saw the beauty of Fermis, but it took me that many years. So I don't expect you to not hate them, but you'll survive them. And maybe someday you will see their inherent beauty. Work